system.
German system, grazie.
Ready? Our speaker today is Umberto Zannier, who will deliver the Hermann lectures. And the first lecture is an overview of some problems on unlikely intersections.
Thank you very much, and I say I'm of course greatly honored for this generous invitation, and I deeply thank this institution for this. So I focused the lectures on some problems which have been the object of recent work, but also have shown connections with previous results and conjectures. So I shall try to give an overview of some of these problems, and focusing especially on a method which arose recently and led to some progress on some problems. So I shall not be in any sense complete, and I limit to the things with which I am more familiar with. So also in this overview I will give sketches of proofs and ideas rather than fine details. In this first lecture I will give a somewhat detailed list of what I shall treat in the next ones. I have planned a total of 4 lectures, and also I shall write notes on these lectures. I gladly accept the proposal to for publishing notes of the lectures. So let me first say just a few words on the title of Unlikely Intersections.
It's hard to say. Can just break
Yeah, I will try to. So this has to do with a simple expectation, namely the following one. Suppose that we have varieties x and y, and say of dimensions of respective dimensions R and S, and say they lie in a space of dimension n, and then we would expect certainly the intersection to be of dimension not exceeding usually. This is at least this, yes, not exceeding this. And in particular, we expect the intersection to be empty if this inequality holds. So this is just the general setting, so to speak. More specifically, also, but in this, well,
so you might be in a fine space,
for example, yes, I'm not thinking to be in a complete space. So if anyway the varieties are taken somewhat randomly, I also expect this kind of inequality, possibly strict if the ambient space does not force intersection to occur when there is equality, for instance. So more specifically, in the problems under consideration, X will be given whereas the Y shall vary in a set sigma of varieties of dimension, of given dimension, for instance, S less than n minus r. And this set will be the numerable. So with fixed x and variable y, and we shall be interested usually in studying the intersection for varying y, and for instance, in asking questions about the union for y in sigma of the intersection. So we would expect this to be small, or possibly finite, unless there is some special algebraic reason for x. But usually this set sigma will be made of varieties with some structure. And usually in all the problems that we shall look at, there will be some special structure on X which shall force some intersection to occur even if it is unlikely. So unless X is special. So in the same spirit, we shall see also that this kind of problem can be rephrased as some kind of local global principles sometimes. In this sense that a point of intersection usually expresses the local properties of coordinate functions on X, for instance, and we wonder whether this property is the specialization of a global property of the coordinates of X. And this global property shall correspond to X being special. And also in the problems that we shall consider, this variety is another thing to be said, that this set of varieties will be the numerable, sometimes consisting of points. And they shall be called the special points. And usually the varieties in this set shall be described by discrete parameters. So they shall admit parameterization, but not continuous, of course, the numerable set of varieties. So it turns out that some known problems of arithmetic and geometry can be put into this very rough context. Let me give some examples. And I shall start from a very simple question posed by Lang in the 60s. It is a kind of a prototype of the general issues to be considered. Lang considered a plane curve defined by plane curve in a affine space, for instance, and seeked solutions in pairs theta zeta of rods of unity. The field, let us think, it may be the complex field or algebraic numbers. For the problem, we look at the problem over a field of characteristic 0, say. But we can think of a complex field or Q bar. It is equivalent because we seek solutions in algebraic numbers anyway. So Lang posed this question. We may look at this as a kind of trigonometric Diophantine equation. If we express the rods of unity in terms of the exponential, we just look for rational values of the arguments in both components. So, and there are, well, we can ask whether there may be infinitely many such points on the curve, on the given curve. Of course, these points, we observe that these points here, they are the torsion points in the algebraic group GM square, which I simply recall. I define this simply GM like the affine line deprived of the origin. And I think of this as a group of points with component-wise multiplication. So these are the torsion points, and they constitute the spatial points in this problem. So we usually expect, of course, if there is no special reason, we expect only finitely many. Lang expected only finitely many such points, unless f is of the following shape. Let us suppose f to be irreducible. And of course, if we have an f of this shape, where here I think of n be arbitrary integers, even negative, the 0 does not affect this problem. And if this rho is a root of unity, then clearly there are infinitely many such points on the curve. Excuse me? Not necessarily. They must be coprime if f is supposed to be irreducible. But anyway, even in any case, we find infinitely many torsion points on these kind of curves. And Lang's question was whether the converse was true, and this was soon confirmed with simple and nice proofs given by Hara, Serre, and Tate. I shall recall them in the next lecture. So in these terms, we have, you see, this shape is the spatial variety for the problem in question. And we may observe that this is highly relevant with respect to the group structure, because this kind of function defines the zero set, defines an algebraic, defines a coset of a subgroup of GM squared, and the coset is algebraic by definition. So in this case, the spatial points are the torsion points, and the spatial varieties are the algebraic cosets, and more precisely the torsion cosets, by which I mean the translate of an algebraic subgroup by a torsion point. This is one of the basic questions which motivated many other ones, and this is somewhat the starting point. So let me give now a more detailed summary of the lectures. So in the second lecture, tomorrow, I shall discuss briefly this problem of Lang again, and see what happens in higher dimensions. Here, the result, I may state it even now, is that there is this statement, and says the following: the Zariski closure in GM, in any power of GM, of a set, an arbitrary set of spatial points, is a spatial variety. Where here spatial means a finite union of torsion cosets. So this was a conjecture, originally a conjecture of Lang, which was proved by Laurent and independently by Sarnak. And then Lierde also worked on this. And it may be proved in a number of ways. Also going back to results on the structure of linear relations among roots of unity. This goes back to Mann and Conway-Jones. And this conjecture of Lang formed actually a part of a deeper conjecture concerning the intersection, this time of X, rather with the torsion points, the spatial points, but with the more general set, namely intersecting a given variety with a group of finite rank. And when the rank is 0, we have, of course, the torsion points. And this was distinctly deeper. And also I may mention there are analogs for abelian varieties which are deeper also. The exact analog of the problem of torsion points for abelian varieties is the natural generalization of the what is called the Mannford Conjecture. This conjecture predicted originally the finiteness of the torsion points on a curve of genus at least 2 embedded in its Jacobian. And it was proved by Renaud, who soon after the proof of the original statement proved the analog of this statement of Lang. This is of a deeper nature. So I may say I shall not touch in this lecture this problem of the group of finite rank, which leads to entirely different methods and ideas. I shall discuss a recent proof of the Mannford conjecture in lecture 3, however. So, and another development that I shall not touch again, however I want to mention it, of this problem of Lang is the Bogomolov conjecture, which has been proved both for the multiplicative case and the general semi-abelian variety case by a number of people, starting with Zhang and then Ulmo and others. So this has to do with an extension of the problem in which we do not look only at torsion points, but at points with small height. So this is another development.
The papers arrived at the annals in the incorrect order.
Yeah. Yeah, and this was mainly for the multiplicative. Yeah. And then Zhang again. And also Superiore, yes. So, okay, so these are some of the developments. However, I will touch only the Mannford Conjecture in lecture 3, whereas in lecture 2 I shall discuss the following other generalization, namely, again, x is fixed, and now in the Lang's problem we intersect x with the torsion points, and the torsion points, the union of the torsion points form the union of the points of the algebraic subgroups of dimension 0. So the idea is now to intersect x with algebraic subgroups of higher dimensions. So G here is an algebraic subgroup, again of Gm to the n. And for the intersection to be unlikely, if it exists, I usually suppose that the dimension of G plus dimension of x is less than n. So this problem was studied, for instance, for a curve in joint work with Bombieri and Masser. In 1999. And we proved two kinds of results. The first result actually concerned the almost likely intersections. So the intersection of x with so the case where the dimension the G has codimension 1. And the x is a curve now. So it is very easy to show that for varying G, we have an infinity of intersections. This is very easy. However, these intersections are sparse, and we proved that the height in this union is bounded, provided x is not special. And here the meaning of special is a bit different. So if x is an irreducible curve, by special I mean that it is not, by special I mean that it is a coset. An algebraic, it is contained in a proper algebraic coset. So if X is not contained in a proper algebraic coset, these points are infinite in number, but they have bounded Weil height. This is some information, actually, because a priori it is not even clear that such points exist in the complementary set. I mean, this could cover everything a priori. Let me observe that how this may be seen as a kind of local global principle. This is because of this. It is not difficult to prove that every algebraic subgroup of Gn to the n is defined by finitely many equations of the type, of the following type: x1 to the a1, xn to the an equal 1. So finitely many binomial equations. So each of these equations expresses a multiplicative dependence among the coordinate functions. And to say that x is not special means precisely that the coordinate functions on x are multiplicatively independent modular constants. This modular constants comes from the fact that we assume that it is not in a proper algebraic coset. And whereas the points in these intersections are just the points where the values of the functions become multiplicatively dependent. So the result asserts that if the point has sufficiently large height, then if the functions are independent, in the strong sense to be independent modular constants, then the values are also independent. So this was the first result. And the second result was for the unlikely intersections. So the really unlikely intersections are obtained by taking G of codimension 2. So again, under the same assumption, if X is not special, then the union over all the algebraic subgroup of codimension at least 2 is finite. So this will be part of the second lecture. And then I shall briefly discuss some developments on these results. And also I shall mention that these results form a small part of a conjecture which was posed by Zilber in 2002 with completely independent ideas. He was seeking a formal theory of the exponential functions in abstract fields. And he looked at the Schanuel's conjecture and arrived at a general conjecture, so was completely on a different path. He arrived to formulate a general conjecture which I will state precisely tomorrow, but let me just say it is this conjecture predicts a certain finite description for the unlikely intersections. In the context of multiplicative groups. Okay, and then another conjecture for abelian varieties, similar one was done by Pink. So this is what I shall discuss tomorrow. Now let me go to third lecture. It is entitled Unlikely Intersections in Elliptic Surfaces and Problems of Masser. In fact, let me start with a problem formulated by Masser for the Legendre elliptic curve. So we take this elliptic curve is defined by this equation. Here we shall think both ways of lambda either as an indeterminate and then this equation defines an elliptic curve over the field Q of lambda. Or we may look also at this equation as defining a surface. So lambda can also be thought as varying over the complex numbers different from 0 and 1, and then we obtain a surface, an elliptic surface. So elliptic in the sense that this surface has the map lambda to P1, to the line, and the fibers of this map are elliptic curves, if we stay out of 0, 1, and infinity. So Masser, his problem was very basic, so he just took a simple example, and I will do the same in my lecture. So I will take the following 2 points on this elliptic curve, which I call P lambda and Q lambda. The first one is simply the point, one of the points with abscissa 2, and the other one with x equal 3. And of course, there will be a corresponding y for some determination of the square root. So we have these 2 points. It may be checked very easily that none of these points is torsion. Is torsion on the curve viewed as over a curve over Q of lambda. And the problem of Masser was what can be said about the set of complex lambdas such that both points become torsion. So let us call this lambda naught to distinguish it from the indeterminate. Become torsion on the elliptic curve, which I obtain specializing lambda to lambda naught. Of course, I avoid 0 and 1. Want to find it, yes. And it is not too difficult to see, and as one can easily imagine, that for each of the 2 points there are an infinity of lambda of complex values such that the point becomes torsion. But of course it is unlikely, we don't expect that the same lambda naught occur for both points. The thing can be put into the context that I told at the beginning in the following way. We can take this surface, I denote it by E lambda, and we can take its square over P1. So this thing here is a threefold. And the the pair P lambda Q lambda as lambda varies describes a curve here. And also each of the conditions, if we take two integers m and n, two positive integers, each of the conditions, so the simultaneous conditions this is the origin in E lambda. This condition also define a curve which depends on m and n. So we have an infinite number of curves, and we expect the intersection will be usually empty, and so we expect finiteness by taking the union. Of course, here we are tacitly assuming that the points here are given, and it may be verified rather easily actually that this curve is not special. If in place of these points we took two other points, what would be the special curve? The special curve would be defined by an equation like this. So by a linear dependence, a non-trivial linear dependence of P lambda and Q lambda, fixed linear dependence with Mn not about 0. So the special curves for this problem are defined like this. So let me point out that that this problem of Masser can be seen as a relative version of the Mannford problem. In fact, let us take in place of the Legendre curve, let us assume that E is a given elliptic curve. And we consider the product E square times P1. And we again may take now 2 points for each lambda in P1. We may take 2 points, P lambda and Q lambda, with coordinates in E over the algebraic closure of Q of lambda. And then the pair of points describes a curve, and looking for the lambdas which give rise to the torsion points then means simply to find the torsion points on this curve. And this is a special case of the Mannford conjecture, which is a theorem of Raynaud. So in lecture 3, I shall sketch the solution of this problem of Masser with the method. So again, lecture 3. Has been obtained jointly with Masser. And with this method that I was mentioning at the beginning, and this same method leads to also to a proof, a different proof with respect to the known ones, which are several, by the way, of the Mannford conjecture. And this has been obtained jointly with Pila. And of this method, let me just say a couple of words. now. So let us think of the Mannford conjecture. So we have an abelian variety. And we have a subvariety. For instance, a curve. Let us think of a curve. And we want to show that X contains only finitely many torsion points unless it is the translate of an abelian subvariety of an elliptic curve. So the method starts from the transcendental uniformization that we obtain for the abelian variety as a quotient C modulo lattice. And if we take a basis of lambda and we see that the torsion points on A may be thought as rational points here. They correspond to torsion points. Rational points with respect to a basis of the lattice. So, and now we look at the curve in A, and also we take the inverse image, and we obtain, we may take the inverse image here or even in, oh sorry, here there is G, which is the dimension of H. So this will be a complex curve if we take the inverse image in C to the G, and it shall be transcendental, we expect, because this map is transcendental. And now there is a method. The first point of the method is to estimate the number of rational points in such a transcendental curve, of course in bounded regions. And there is a method which originates in a paper of Bombieri and Pila on 1989, I believe. And this paper contained for the first time uniform estimates for the number of rational points on curves, on algebraic curves, but also on transcendental curves. And this was also motivated by a question of Sarnak. And this method was further developed to varieties of higher dimensions in work of Pila and Pila-Wilkie. So the principles are already in this paper, but the development to higher dimensions required additional tools. And so one can use these estimates to bound the number of points in bounded regions of this transcendental curve. There are things to do before one has to throw away the possible semi-algebraic arcs contained in such a thing, but it turns out that there are no such semi-algebraic arcs. So once this verification is done, one can apply these estimates of Bombieri, Pila, Wilkie. And one obtains that there are not too many rational points of a certain height, of a certain, so with the numerator and denominator bounded by a parameter t. There are at most t to the epsilon such points. And now we go back to the algebraic ambient. And so we take a possible torsion point of high order on A, on X. And the idea is now to conjugate, to take algebraic conjugates. If we conjugate the points with the elements of the Galois group of the field of definition of X, these conjugates will continue to lie on X. and they will provide other rational points on these x tilde. Torsion points of the same order. Yes, this is crucial. Of the same order, which corresponds to rational points of the same with the same denominator in the x tilde. So now, if we have a lower bound for the degree of the torsion points, so the number of conjugates, we can compare the estimates and hopefully deduce a contradiction for large enough order. And these lower bounds were already ready due to work of Masser by transcendence methods. He obtained lower bounds which are polynomial in terms of the order. And so the comparison of estimates leads to a contradiction. And it turns out that the method can be also applied to the variable situation, so providing also a method suitable for this problem in which the elliptic curve is varying. So let me now go to the fourth lecture. Yes.
Of an elliptic surface, you have a family of abelian varieties. The results are still okay?
They should, but if the family of abelian varieties varies, we have nothing in general except in the two-dimensional case. So in the last lecture, I shall say something about the so-called conjecture of André Oort. Now I skip the formulation of the conjecture, but let me just say that it has the same structure as the statements that we have so far seen. So in the André Oort conjecture, we have Shimura varieties. I will make an example soon. In place of, so up to now I have discussed multiplicative groups and abelian varieties. And we also have special points, which here are the torsion points. And we again have a notion of special subvarieties. Which here are the torsion cosettes and the finite unions. And the statements that we have seen may be put into the pattern that, for instance, there are many phrasings possible. But that, for instance, the Zariski closure of any set of special points is a special subvariety. And this is the formulation that the André Oort conjecture has. So let me just give simple examples of, the simplest examples of Shimura varieties, I believe the simplest one are given by modular curves. These modular curves, they parameterize elliptic curves with additional structure. For instance, there is a modular curve parameterizing elliptic curves and the choice of a subgroup of a given order of the curve, and so on. And the simplest of these modular curves is, the simplest one is a curve which parameterizes just elliptic curves. It is the affine line, simply, as a variety. It parameterizes elliptic curves in the following sense. If we take an elliptic curve and we write over the complex numbers, and we write, for instance, a Weierstrass equation of this shape, then we associate to the curve its invariant J, which is defined in this way. So we obtain simply a complex number. And it is, of course, well known that if two equations give rise to the same invariant, then they become isomorphic over C. So this J actually parameterizes the elliptic curves, the complex elliptic curve up to isomorphism. And so this is the simplest case, I think, of Shimura variety. And what are the special points? For this case, the special points are given by the values of J, which correspond to elliptic curves with complex multiplication. This means that the endomorphism ring of the curve is larger than it is usually, namely it is larger than Z. And these values are algebraic numbers, actually algebraic integers, they are known to be. And they are known to be the values J of tau, where now J is the modular function. This is a remarkable function, and they are the values J of tau, where tau is a quadratic imaginary number, namely lying in the upper half plane, namely a number of the shape a plus I square root of d, where a is rational and d is rational and negative. So these numbers have algebraic integers and have very remarkable arithmetic properties. So there is a reason for, of course, for defining the spatial points at the CM points, but I will skip for this reason now. So let us see what then some statement of some special case of the Shimura, of the André-Oort conjecture. So for this variety, for this modular curve, there is no non-trivial André-Oort conjecture, because the variety is simply A1 and there are no subvarieties, only points. So the André-Oort conjecture is in this case trivial. But it becomes non-trivial if we take an analog of Lang's original question. So if we take a product of two affine lines, so this is also a Shimura variety, and we think of the A square as parameterizing pairs of elliptic curves. And now let us take a curve, a plane curve, again defined by some equation, some polynomial equation f(x,y) equal naught. And the problem is now what can be said if there are infinitely many CM pairs. Let us call on this curve. So this is the curve. So this is the exact analog of the problem of Lang for the torsion points. This was considered by André and actually solved by André. He proved that one of the following occurs. So if there are infinitely many pairs and the curve is irreducible, there are the following cases. Either x is a horizontal or a vertical line. So one of the two coordinates is fixed and equal to a CM point. Or x is a modular curve. Of the type y naught of n for some n. What are these modular curves? Well, they are constructed in a certain way so that they are the equation of the curve is satisfied identically by the function by the pair j of tau, j of n tau, where tau varies. So this pair lies on y naught of n, where j now is the modular function as before. And this curve parameterizes the pairs of elliptic curves such that there is an isogeny of degree, a cyclic isogeny of degree n between them, this is a symmetrical notion. So what does this mean? That if J1, J2 lies here, then the elliptic curves with invariants respectively J1, J2, there is an isogeny, a cyclic isogeny of degree n between them. And the existence of this isogeny forces the fact that if one of the curves has complex multiplication, the other one must also have. So these are true exceptions, true special cases. And André proved in a very nice proof that this is they are the only examples. So in the lecture 4, I would plan to give a very brief sketch of André's proof, but then I would like to compare this with Pila's proof. Pila adapted the method with adding to this method substantial tools of his own, the method that we previously employed and that I have mentioned in connection with lecture 3. He found that the method may be applied to the André Oort bunch of problems, and obtained not only a new proof of André's result, but a very significant generalization which was unknown up to now. Let me say that the complete André Oort conjecture has been recently announced by Ulmo, Klinger, and Yafaev. However, under the generalized Riemann hypothesis, which was yeah, but now in fact this hypothesis appeared already in a series of papers of these authors and Edith Soven also. So and there were very few unconditional proofs of cases, perhaps essentially the only one, yes. And now Pila has given an unconditional proof of the general case of any power of the affine line, and what is also relevant is that one can mix the Andrea-Oort conjecture with the Manin-Mannford and the lungs. And I would like to stress that mixing them is not just having the union of the statements. It is distinctly, it was considered more difficult. So this I shall briefly discuss in the last lecture next week. So thank you very much.